When we model rate laws, we use the basic premise of a collision model for the reaction. That is, there's an unperturbed or undisturbed reaction taking place where we're not interjecting anything like mixing or turbulent flow. This is just something like a reaction sitting in a beaker allowed to occur on its own. When we talk about the collision model, we base factors such as frequency of collision, the number of collisions that occur with the right amount of energy to allow the reaction to occur, also known as the activation energy, or the energy required to break the strongest bond in the chemical reaction. We also have to take into account that the reaction occurs with the right orientation. If you think back to the first video where we had two molecules colliding, we found that depending upon how the molecules hit, we may just have a collision and they bounce off each other, or we may have a chemical reaction where the bond actually breaks. So when we build into our collision model, we take into account temperature. Increasing the temperature always has the effect of increasing the rate of a reaction. And the reason for that is by increasing the temperature, you're increasing the amount of kinetic energy a molecule has, and the more kinetic energy a molecule has, you have a better chance of breaking the toughest bond in the reaction. So you always have to have at least the activation energy in order to have a reaction occur. In an environment such as ours, all forms of carbon should exist as carbon dioxide. We should all be spontaneously combusting. There should be nothing but a greenhouse gas floating around in the atmosphere, and that's it. Why don't we all spontaneously combust? Well, it turns out the activation energy is pretty high to get spontaneous combustion of carbon, fortunately for us. So we always have to take into account how much energy it takes to break that toughest bond in our activation energy. If we don't have that energy, then we can't get over the barrier, so the reaction won't occur in that instance. So we have to have the collision, it's got to have the right amount of energy, and it has to have the right orientation. We can bring all these factors in to create what's known as the Arrhenius equation. The Arrhenius equation is actually a way of determining what the rate constant K is based off of the activation energy. So the rate constant K equals the collision factor or the frequency factor, which is a combination of how many collisions you have and do they have the right orientation, and is also generally temperature independent. We find that we have that raised to the power of E. We have the negative activation energy, and I'll just point out activation energies are always positive values, so the equation is forcing EA to be negative, but all activation energies are positive, divided by the gas constant and the temperature in Kelvin. This is all part of that exponent, negative EA over RT. So the rate constant is used to determine the activation energy. When we find the activation energy, we do an experiment at several different temperatures, and what we do is based off of the rate constant at any given instant, we can make a plot of the temperature dependence and the rate constant K. And we can do a little bit of manipulation, but I'll just give you the take-home message that if you make a plot of the natural log of the rate constant K as a function of 1 over the temperature in Kelvin, if your experimental data is good, you should get a straight line. And that line has a slope of the negative activation energy over the gas constant R. So when you see a plot like this, multiply the slope by 8.314, get rid of the negative sign, and you'll find you have your activation energy. Activation energies are typically in the realm of kilojoules per mole, tens to hundreds of kilojoules per mole, and they're always a positive value because it always takes energy to break a bond. And it doesn't matter if a reaction is endothermic or exothermic, you always have this transitional state, which we see at the top of the peak in these cases, where the molecules collided, it's got enough energy to make it over that energy barrier, and it's been an uphill process to that point. and maybe you'll get all your activation energy back and a little bit more if the reaction's exothermic, like cases 1 and 2, or you may not recover it all in case 3, which means it's endothermic. Between these three reactions, the reaction we would predict to have the slowest reaction rate would be reaction 2. It has the highest energy barrier. Doesn't have to do anything with the fact that the reaction's endo or exothermic. It's simply the elevation or how high the activation energy is, which determines how fast the reaction occurs. We would also predict reaction 1 to be the fastest one because it has the lowest activation energy. Now, activation energies can be altered by something known as a catalyst. A catalyst is something that always lowers the activation energy of a reaction, resulting in an increase in speed of the reaction. What a catalyst does is it actually changes the series of steps by which the reaction occurs, which is the result of having a lowered activation energy. That is, changing the steps by which the reaction occurs, if it's a catalyst, always lowers the activation energy, thus it always speeds up the reaction. It's also worth noting that when you have a catalyst, while the catalyst takes part in the reaction, you actually recover the catalyst at the end of the reaction. As you see in the blue line there, when you have hydrogen peroxide in the presence of bromide ions and hydronium ions, at the end of the reaction, we see those same bromide and hydronium ions present in the end state, along with the original products of water and oxygen gas. So a catalyst is something that alters the speed of a reaction. A catalyst is always recovered when the reaction is finished, and it always speeds up the reaction. Now, catalysts can be in the same phase as the reaction, or they can be in a different phase. You can have homogeneous and heterogeneous catalysts. Regardless of whether it's homogeneous or heterogeneous, the catalyst always helps breaking up the toughest bond by altering the mechanism. Finally, we see catalysts in the form of enzymes. Enzymes are simply biological catalysts, which are designed to fit to particular molecules and cause them to break rather quickly and easily. Without enzymes, we would still be waiting to digest lunch from when we were 5.